Okay, so we were on the end of question number 3, which on the top we're going to end up with negative, oops, good if I had, negative 3,025 meters squared per second squared, and that's going to be divided by negative 22 meters per second squared. And when you do this, you should get 137.5 meters. Okay, for number 3. Number 4 says, starting from rest, a car accelerates. So starting from rest, VI is 0. A car accelerates for 10 seconds, delta t is 10 seconds, until it covers a distance, delta d, of 150 meters. What is the acceleration? We're looking for A. So what equation do you have that has a VI, a delta t, a delta d, and an A in it? It would be delta d is equal to VI delta t 1/2 A delta t squared. Starting from rest, that means this whole front term will be 0. And so you can cancel it all out before you even start to rearrange if you want, and it'll make your life easier. You want to get the A alone. If you didn't cancel this out, then you'd have to subtract it. But since we did cancel it out, we want to get the A alone, multiply both sides by 2. So 2 delta d equals A delta t squared, and then divide by t squared. So you would get A equals 2 delta d over t squared. So 2 times 150 meters divided by 10 seconds squared. 300 on the top divided by 100 on the bottom. A is equal to 3 meters per second squared. Number 4. Number 5 says, a person wearing a shoulder harness can survive a car crash if the acceleration is smaller than negative 300 meters per second squared, meaning he's slowing down, it's opposite motion. Assume this constant acceleration. How far? You're looking for delta d. How far will the front end collapse if the car crashes going 101 kilometers per hour? So VI is 101 kilometers per hour, and when you switch 101 kilometers per hour to meters per second, you get 28.05 with the 5 repeating. So just like as a point of interest, like here's the wall, not a point of interest, but just so we know, we understand. Here's the wall, here's the car. Okay, so there's a person, for some reason unknown to us, driving the car into the wall. So when it just touches the wall, it's going 28.05 repeating meters per second. When the front end touches, the wheels are still moving, and they're going to keep moving until the car comes to a stop. 0 meters per second. And so the question really is, like, how far do these wheels move before they come to a stop? And how far the wheels move is then how far the front end crumples. Okay, so we have an A, a VI, a VF, and we want a delta D. We don't have any time, so you would use the equation that doesn't have time up there. VF squared equals VI squared plus 2A delta D. And you're looking for delta D. Okay, so bring the VI squared over by subtracting it. And then to get the delta D alone, divide both sides by 2A. So you'll be left with delta D equals VF squared minus VI squared over 2A. VF squared is going to be 0. So it'll be negative 28.05 repeating meters per second squared over 2 times negative 300 meters per second squared. Okay, so a minute ago you would have found your VI in the calculator. Don't clear this. Use it. Just square it. Okay, and it's a negative because the negative is outside. And now you're going to divide by 2 times 300, which is 600 negative. And you're going to get 1.31185 So we would probably say 1.312 meters. All right, that is number 5. Number 6 says engineers are developing new types of guns that might someday be used to launch satellites as if they were bullets. One such gun gives a small object a velocity of 3,500 meters per second, moving it for only 1.14286 times 10 to the negative 5 seconds, roughly. Okay, now what is this 3,500 meters per second? If the thing is launching it, this must be its final velocity, because usually when you launch something, its initial velocity is 0, right? So initially it's not moving, and then this thing applies a force on it to accelerate it to a speed of 3,500 meters per second. What was the acceleration given to the object? Okay, and then over what distance? So first, the acceleration, you can just use A equals VF minus VI over delta T. So A equals 3,500 meters per second minus 0, or you can just do this, over 1.14286 to the negative 5 seconds. So on your calculator, 3500 divide by 1.14286, and then use your EXPE button or times 10 to button, negative 5, press equals, and you should get 3. It's a big number. Second function, I'm going to put it in scientific notation. 3.0625 times 10 to the 8th. A is equal to 3.0625 times 10 to the 8th, and it's going to be meters per second squared. Meters per second divided by seconds is meters per second squared. Okay, so that's my acceleration. Now it wants my delta D. Well, I have my A, I have my VF, I have my delta T. So I could do delta D is equal to VI delta T, 1/2 A delta T squared. The VI is 0, so this term disappears. So delta D is equal to 1/2. The A we just wrote down, 3.0625 times 10 to the 8th meters per second squared. And then we're going to multiply that by our 1.14286 to the 5th seconds, and don't forget to square it. So again, in your calculator, you have your acceleration all out there with all the decimals. So don't clear it. Just do times 0.5 times 1.14286 EXP. Whoops, and that's a negative. Negative 5 squared equals. And you should get 2.0, a lot of zeros, times 10 to the negative 2 meters. Really, that's 2 centimeters. Okay? And if I were to look at significant digits in all of these, 4, 3, that one has 6, so I didn't keep too many. I could keep a few more zeros there. Okay? All right, so that's it for your homework from last night. Hopefully these are getting better. I'm going to show you one new little piece with these equations. Not a new equation, just a new little piece to work on. Okay?